All right, so let's continue with network core. We are still using the slides from the book Computer Networking, a top-down approach by Jim Kurose. So we are going to talk about network core, packet circuit switching, and the internet structure. So in order to understand the network or the internet, we should look at the network core. So this is a mesh of interconnected routers, right? So we talk about the endpoints. Now we are talking about the network core. There are a lot of routers, local or regional internet service providers, and they're connected to each other somehow so that we can connect the whole world. So let's talk about how this works. So how the packets are actually transmitted through this system. So packet switching, hosts break application layer messages into packets. Network forwards packets from one router to the next across links on path from source to destination. So idea is simple. You are at the edge, you are a host. So you divide your packets, send it to the network, and network somehow sends this to your destination. So two key network core functions are as follows: routing algorithm. So this is actually a table. Every router has some kind of a algorithm to determine to create this table. So for instance, in this router, we're assuming that the input comes from here. So you have actually 3 links, and you should know which link to use and send this packet to. So this is actually determined from this forwarding table. Of course, we are going to talk about IP and TCP. So we know the router will know actually where the destination is somehow. So he knows which router to talk to so that it will reach the destination. So this is called forwarding, also known as switching. Local action is as follows: move arriving packets from router's input link to appropriate router output link. So by appropriate, the router somehow should know where to send it to. So this is actually what this forwarding table is used for. So global action is follows: determine source destination paths taken by packets or by the routing algorithms. We actually, determine where each source and destination is. So here's a simple analogy to explain by the book. So here from this city to this city, we call it routing because so actually the analogy is as follows. For instance, you are starting from San Jose and want to go to Northampton. You have a specific address, the street, the building number, the apartment number, but saying this apartment number or the street, people here does not make sense, right? So you want to go to this city, you don't know which road to take, so you ask a person here that tell you which road to take, but they also tell you, and after some point on, ask another person where to go. So you take this road to reach Northampton, but when you reach there, you have to ask other people, so which street you should go and so on. So this is routing, but when you reach the city, we will refer to it as forwarding, right? To where to go and from, and so on. So packet switching works as store and forward. So here is the router. You are sending packets. You divide it into L bits, and router first stores. So by store we mean as follows. Assume that, let's say that this L is 100 bits. So a router actually can send it when it receives the first bit of this 100-bit packet, right? But it doesn't work like that. The router waits for the whole L bit, or in our example, 100 bit to reach, because it has to check if it is, proper and so on, then sends it. So it is a store and forward operation. So here we're assuming that our links can transmit R bits per second. So packet transmission delay takes L divided by R seconds to transmit. In other words, push out L bit packet into link at R bit per second. So one hop numerical example. So here in our example, L is 10 kilobits, R is 100 megabits. So one hop transmission delay is L divided by R, which is 0.1 milliseconds. Okay. As I mentioned, store and forward is as follows. Entire packet must arrive at router before it can be transmitted on the next link. Okay. So if a lot of more packets are reached to the router, then they have to wait into queue. So this is what we call queuing. Queue of packets waiting for transmission over output link, because maybe packets are arriving a lot faster than your the speed of your link, so they have to queue up here. So queuing occurs when work arrives faster than it can be serviced. And this can cause sometimes loss. If arrival rates in bits per second to link exceeds transmission rates of link for some period of time, in this example, this is what is going to happen. Because the link is slow, you can transmit 1.5 megabits per second, but hosts are sending a lot faster, like 100 megabits per second. So they have to queue here, but this is a device with finite memory. You cannot store all of them here. So when your buffer is full, the new coming packets has to be dropped because there is no place to write them, store them in your buffer. So packets will queue, waiting to be transmitted on output link. Packets can be dropped, lost if memory buffer in router fills up. And this happens in practice a lot of the time. So instead of packet switching, to avoid this kind of queuing and packet loss, you can do another approach, which is circuit switching. So in this scenario, for instance, this computer wants to connect to this computer, and there is a physical path for them. So we actually allocate this path and reserve it for these two devices to communicate. Okay, actually, this is what happens in phone calls. This is why there is no delay when you're calling somebody, because if if there isn't any interference and so on, your voice reaches to that person instantly. But if you are making a WhatsApp voice call or video call or Zoom call like this, sometimes due to our connection speed or the packet queuing and so on, the voice or the video might come a little bit late. This is the main difference between WhatsApp call and the GSM call, because one of them is circuit switching, where you reserve the circuit for them so that this transmission rate is fixed and you can send and receive data using that circuit. Okay, so end-to-end resources allocated to reserved for call between source and destination. In diagram, each link has 4 circuits, as drawn like this. Call gets second circuit in top link and first circuit in the right link. Okay, since you reserve them, nobody else can use it. That is the catch. Dedicated resources, no sharing. This is what I tried to explain. Circuit like guaranteed performance. Circuit segment idle for if not used by call, no sharing. So you call somebody, for instance, but you're not talking, but you're on the phone. So actually you're not transmitting any data, but you are using that line, so nobody else can use it. Commonly used in traditional telephone networks. And in the circuit switching, we can do 2 different multiplexing, mainly frequency division and time division multiplexing. In the frequency division, this optical electromagnetic frequency is divided into narrow frequency bands. So in this example, assume that we have 4 frequencies. So this can support up to 4 users. Right? Each call allocated its own band can transmit at max rate of that narrow band. So here you allocated 4 frequencies to 4 users. So if this is a telephone line, the 5th person who wants to call somebody actually has to wait for these 4 people to stop communicating so that you can use that frequency band. So this is what happens actually during concerts and so on, because there are a lot of mobile phones and the GSM base station cannot allow all of them to, use the phone lines. Time division is a little bit different than this, because this time the time is divided into slots. So here, each call allocated periodic slots can transmit at maximum rate of wider frequency band only during its time slots. So this time, for instance, blue user uses the whole bandwidth, but has to wait 3 time slots to transmit the second data, and so on. Okay, so one of them is frequency division, another one is called time division multiplexing. So this way, in each scenario, you allow 4 people to communicate. Of course, you can divide it into more, slots, so you can allow more users. But if you allow a lot of users, then the time between your first allocated slot and the next one increases. So this will cause some problems. So this is why you cannot, allow infinitely many users to use time division multiplexing. Okay, so let's compare these approaches, packet switching versus circuit switching, because circuit switching looks a lot nicer because it is a guaranteed link. And, for instance, in this example, we will see why packet switching is used on the internet instead of circuit switching. So assume that our router is connected to internet service provider with a link that supports 1 gigabits per second, okay? And we have end users. All of them are using this link. So this link actually have to be divided between all of these end users. And if you want, for instance, each user to have 1 megabit per second, then n can be at most 10, because, if you divide 1 gigabit per second with 100 megabit per second, the result is 10. So you can, allow only 10 users to use this link. So the question is, how many users can use this network under circuit switching and packet switching? And in this scenario, as the example says, not every user are active all the time. They are active 10% of the time. Think about it in this way: your computer is connected to the internet, but you don't use it 24 hours, the whole day, right? You use it from time to time. So, it is a probabilistic approach. We're assuming that every user is active 10% of the time, just 1/10 probability. So how much can you support? As I mentioned, circuit switching in this example can support at most 10 users, because 1 gigabit per second link, and you want each user to have 1 megabit per second. This way you can allow only 10 users to use it. But in the packet switching, it allows this. I'm telling the solution. It allows 35 users, because the probability of more than 10 people active at the same time when n is 35 is less than 0.0004 probability. So of course, you would like to ask, how did you calculate it? Actually, this is just a simple combinatorial or probability theory example. I encourage you to solve it, but question is, let's say that you have n users. What is the probability of only 0 users are active, because all of them is active with probability 1/10. So you can calculate it. The probability of only 1 user is active, 2 users is active, and so on. So you can calculate these probabilities. And when you choose n as 35, the probability of more than 10 active people at the same time is less than this probability. So it rarely happens. This means that you can allow 35 people here, and from time to time, more than 10 people will be active. So they will be queuing here, so they will not reach 1 megabit per second, but still, compared to 10, 35 is a huge number. All right, so is packet switching a slam dunk winner? Great for burst data. Sometimes has data to send, but at other times not. Okay, and this is actually what happens. Sometimes you download a huge amount of file or uploaded file, but then maybe you stop using internet or just use it for surfing and so on. So it is good for resource sharing, simpler no-call setup. Excessive congestion possible, packet delay and loss due to buffer overflow. Protocols needed for reliable data transfer, congestion control. This is why we will call about TCP. How to provide circuit-like behavior with packet switching. It is complicated, and we will study various techniques that try to make packet switching as circuit-like as possible. This is actually why we are, good communication when we have voice calls or like Zoom calls like this. Human analysis of resort resources, circuit switching versus on-demand allocation packet switching. So the book actually asks you, do you have any idea about human analysis? And one example they give is as follows. For instance, when you want to go to a restaurant, some people, call and reserve it, right? So if everybody makes a reservation, it is like circuit switching. So all of the tables are allocated for people who made a reservation. So you go there and you sit down and order your meal. But in the packet switching, you don't make any reservation. You go to a place. So if it is empty, you sit down. But if it is not, then you have to wait in the queue. So this is the human analogy for this packet switching and circuit switching. So on the internet, we use packet switching. Hosts connect to internet via access, internet service providers, ISPs. So every country has this kind of internet service providers. It can be companies, it can be universities. So access ISPs in turn must be interconnected so that you can connect the whole world. Yeah, so that any two hosts anywhere can send packets to each other. Resulting network of network is very complex. Evolution driven by economics, national policies, and we should just make a look at it and understand how the current structure of internet works actually. So initially assume it like this. So you have a lot of access points. So without internet service providers, these devices can try to connect each other, but this is a very hard problem. For instance, if there are n access nets in this picture, so this has to connect to n of them. So everyone has to connect to n of them. So connecting each access ISPs to each other directly does not scale because it is big O n square connections. Okay, so we have to come up with a solution for this internet service providers. So one solution is having a one global internet service provider connecting all of these ISPs. So this is actually what we can desire, but actually this doesn't work because we cannot trust a single authority to provide internet to the whole world because if something goes wrong, this causes a single point of failure. So instead of that, let's have more ISPs, and they are somehow connected to each other, right? So, but if one global ISP is viable business, there will be competitors who will want to be connected, right? Because here, when you have the global ISP, anything below that will be a customer. You have to pay money to, connect each of these ISPs. So currently, how it works like this, we have this kind of ISPs, but they are connected to each other via internet exchange point. Okay, because we can connect ISPs to each other like this. We can create clusters, but we can also connect them to each other. Right? So sometimes we have, ISPs where it is only dedicated to a country, but sometimes we have regional internet service providers, like, maybe it works in Europe and so, not dedicated to a single country, but works for the region. And another thing is that we also have content provider networks. There are huge companies like Google, which have many data centers. So they try to create their own network, which is not directly, which is actually isolated from the internet, but it is still a network with themselves. So they may run their own network to bring services, content close to end users. Google have, I think, 19 data centers scattered all around the world, and also with some small data centers. So the picture turns something into like this. At center, small number of well-connected large networks. So this tier 1 ISPs are huge companies. I think there are a dozen around, like AT&T and so on. So they connect, ISPs to each other. But there are many. But there are also companies like Google who have their own network. So tier 1 commercial ISPs, for example, level 3, Sprint, AT&T, NTT, they provide national and international coverage. Content provider networks like Google, Facebook, they have private network that connects each their data centers to internet, often bypassing tier 1 or regional ISPs. Okay. So the end picture is like this. So these are ISPs, for instance. Assume that this is our university's ISP, or Turkey, I think Türk Telekom is the internet service provider. So it can be connected to regional ISP, and that in turn might be connected to other regional ISPs by internet exchange points, and all of them are connected to top level tier 1 internet service providers. So the ISPs at the top actually don't pay any money, they provide the service. So anything below it has to pay money to, something above them. So this is how it works. This is actually the reason why there are internet exchange points, because, for instance, this ISP can use this tier 1 to connect to this ISP, but actually, instead of paying that amount of money to this, they can create an internet exchange point where this ISP can connect to this ISP. This is actually related to economics. Okay, this is why actually this internet exchange point means in this respect. So the money you pay actually depends on the data you are transmitting using this regional or tier 1 ISP. This is why you may want to avoid using them and instead use an internet exchange point. Okay, this will be all for the network core.